So in the last video, we showed that the span of the set of just the single vector 1, 2 refers to the set of multiples of the vector 1, 2, where k is some real number. There's no reason to use k. I think I used a in the previous video. It doesn't matter. And you can think of this as all the points tracing along the line y equals 2x. And so that's one of the things that we saw. And if this is a line through the origin, that means it's a subspace. So that's a line through the origin, and therefore it's a subspace of R2. Likewise, the span of the vectors 1, 2 and 3, 1 we saw was all of R2. So again, just by definition, this is going to be the set of linear combinations, say A times the first vector plus B times the second vector, where A and B are real numbers. Okay, I realized that this funny symbol here I should explicitly write out. Where k is a real number. Okay, so where k is real. And again, we said that this was R2 in the case of the span of the two vectors 1, 2, and 3, 1. A few other things can happen. What's the span of the vector 0, 0? Well, that's going to be the set of multiples of the vector 0, 0, where the multiple that we're looking is going to be a real number. And what is that, of course, but just the single set with the origin in it? Okay, notice that all three of these are subspaces. That's not a coincidence. The subspaces of R2 consist of the lines through the origin, and we could get a different line if we started with a different vector. We could have R2, and it turns out that we'll have the span of two vectors being R2 in certain cases. We'll talk about what has to happen in order for that to be true. And then likewise, the span of a vector could also be the origin itself, could just be the 0 vector. Okay, so these are all subspaces of R2, and that's not a coincidence. Let's go on and let's talk about spans in R3. This is going to be a little bit harder to visualize, but I want to think about what's the span of the vectors 1, 2, negative 1, and 1, 1, 1. So this, just by definition, is going to be the set of multiples of the first vector. So a set of linear combinations of each vector. So it's going to be the set A times the first vector plus B times the second vector, where A and B are real numbers. And so again, I want to jump over to a graphing program and show you how that's going to look. Okay, so let's do that. So this graphing program is going to have the vector, what we're going to do is let's start with just the vector A equals 1 and B equals 1. And then this is going to have the vector 1, 2, negative 1, and 1, 1, 1. And then if we add them up, so if I want, I could add in, so just to make it a little bit clearer what's going on here, we have the vector that takes the origin to the point 1, 2, 1. We have the vector that takes the origin to the point 1, 1, 1. And this is a graphing calculator, so I'm going to pick this up and move this a little bit just so you can kind of see it and feel what this is going to look like. And if you were to add these two vectors, if you were to go tip to tail, and if you were to move, say, this vector, and so that this vector would start at the tip of the other vector, these would add up and give you the sum of the vectors. So this vector that I have here is going to be the sum of the two vectors. Okay. But now what I want to do, so let's get those vectors out of the way. Now what I want to do is I want to think about what are all the linear combinations going to be. And so I'm going to allow each of those vectors to be scaled and then added to each other. And let's think about what's going to happen here. And so I'm going to just let this play. And we'll think about what is this going to look like. This kind of looks like a mess. Are we getting all the points in R3? Well, it's not clear until we pause the process and kind of play around with this set a little bit. It's not clear at all from this viewpoint what's happened, but if I rotate this, it turns out, it's a little strange to see, but it turns out if we rotate this, that all of these points lie along a single plane through the origin. So you could think of a plane as kind of like this infinitely long, super thin sheet of paper in three-dimensional space, and in this case it goes through the origin. Okay, so if we were to look at the graph, this is kind of the graph that we have, but all of those points are along this plane, so they all kind of line up. Okay, so it turns out that two vectors, in this case the set of linear combinations of these two vectors, are going to determine the plane through the origin, okay, containing those two vectors. So let me say that a little bit better. Let's get rid of the pictures here. If I were to take the vector A and B, and you can kind of move this along, it turns out that there's going to be a unique plane through those two vectors. So any plane that does not contain both of those vectors, let me say it a different way. There's exactly one plane that goes through both vectors at the same time. And so that's the plane that turns out to be determined by the span of the two vectors. So, so let's write this because I'm getting a little wordy here. So the span of the two vectors 1, 2, 1 and 1, 1, 1 turns out to be the plane through the origin containing these two vectors. So containing 1, 2, 1, 1, 2, negative 1, and let me make sure that we're emphasizing that these are vectors, and 1, 1, 1. So there's exactly one plane through those two vectors. That is the plane that gets determined by this span of those two vectors. Okay, so this is the set of linear combinations of these two vectors, and that turns out to be a plane through the origin. That turns out to be a subspace. We could do other things as well. So in R3, if we were to look at just the span of, say, the vector 1, 2, 3, what do we think would happen? Well, we're going to have some vector in three-dimensional space. We're going to be allowed to scale it, so it's going to scale, and then we're allowed to point it in the negative direction as well. Okay, and basically along that same line, but in the negative direction, turns out that this is going to be a line through the origin. Okay, and I'll let you figure out exactly what that line is. I don't care about the equation of it. It's just geometrically going to be a line through the origin. Again, that's also a subspace of R3. If we were to take the span of three vectors, as long as no three of them are on the same plane, so let's say we have 1, 1, 1, 1, 0, 0, and 0, 0, 1. Okay, so for example, those vectors would all be fine. Here, the span is going to be R3. Because what we're allowing is we have three vectors in R3, and so we can write every vector in R3 as a linear combination of these three. Let's prove that. So let's show this. So this purple star is what we'll do for the rest of the video. So let's show that the span of this set is going to be R3. Okay, so we'll prove that, or we'll show it. And so I want to think about, let's pick an arbitrary vector, say S, T, R in R3, and then we want to find scalars A, B, C, so real numbers A, B, C, so that STR is equal to A times the first vector plus B times the second vector plus C times the third vector. Okay, and so we want to be able to do this. And again, if we move these constants inside the vectors, if we add all of these up, we're going to end up with three equations and three unknowns. So S is A plus B, T is going to be A, And R is going to be A plus C. Okay, and it turns out that you can actually very easily find solutions here, but we don't really even need to work that hard. You could write these, you could quickly realize that you can parameterize our solutions or even find a set of solutions for arbitrary S, T, and R. But this is really just taking a matrix equation, and the matrix that we're looking at is, let's see, we have 1, 1, 1, B, so 1, 0, 0, 0, and 0, 1. And basically what's happening is that these vectors are becoming the columns of our matrix. So that 1, 0, 0 and 0, 0, 1 are, again, those are the columns of the matrix. You could equivalently write them as the rows, that's fine. And times ABC is going to be equal to the vector STR. And it turns out that this is going to have a unique solution. So this has a unique solution. And how do we know that? Well, we know that because the determinant of A is non-zero. Okay, where this is our A, this is our X, and this is our constant B. Let me write it as a vector so that it's clear what's going on here. Okay, so this has a unique solution because the determinant of the matrix is non-zero, and we know that this system, if the determinant's non-zero, will have a unique solution. That's one of the things that we talked about with determinants. So that turns out to be very useful here because here this means that these three vectors span all of R3. So we can write any arbitrary vector in R3 as a unique linear combination of these three vectors, 1, 1, 1, 1, 0, 0, and 0, 0, 1.